These are the notes for section 9.1, first order differential equations. So, as you'll recall from before spring break, we were talking about differential equations, and we were looking at all the different types of equations that exist with differential equations. We were classifying them. So if you just, if you recall some things that we're talking about, let me just make a few notes here. We classified ODEs, right? So we were looking at the order of an ODE, whether it was linear versus nonlinear. And we were looking at if it's an ODE versus a PDE. So we kind of did that, we did this all before spring break. Just to, give yourself an idea of where we left off. But, so now that we kind of did that, now we want to actually, so just to remember, make a little note here, right? The solution to an ODE is a family of curves. What do I mean by that? So a family of curves. So basically the solution to an ODE is a family of curves. What do I mean by that? That is a family of curves is just another way of saying an infinite set of functions. So remember, the solution to an ODE is a set of functions, whereas the solution to an equation is a set of solutions, a set of numerical solutions. I've mentioned that in class a few times, but that's the idea behind it. So, and I also mentioned this in class as well, that the solution, most differential equations that exist do not have particular solutions. So I'll make another note of that. Note, remember, most ODEs do not have a particular solution. They don't. I've mentioned this in class. The majority of differential equations that exist do not have a particular solution. First order linear differential equations do have particular solutions, and this is just the tip of the iceberg when it comes to differential equations. I mentioned this as class as well. There's a whole course devoted to differential equations, and so you can imagine that we're only looking at a particular, we're only looking at a particular piece of differential equations in Chapter 9. And, we did the classifications before spring break ended. So what we're going to do in this first section is we're going to look at, since we can't find solutions to differential equations, we're going to look at ways we can, see how solutions behave. So we're going to look at what we call slope fields, and we're going to look at another way of approximating solutions, which we call Euler's method. So let me make a little question here. It's a question. How do we measure the behavior of the solutions, and I use solutions in plural because the solution could be singular or plural. So how do we measure the behavior of the solutions to a ODE? And one way we could do this is we create what's called a slope field. So we can use what we call a slope field. It's also called a directional field. Either one is, either one is fine, but we could call them a slope field or a directional field. So if I'm given a differential equation, so before that, but what is a slope field or a directional field? Basically, slope fields I'm just trying to think of the best way to say this. Slope fields measure the behavior, or I'll say this, the long-term behavior of solutions to a given ODE. And that's the idea behind these things. So, when you're making a slope field, so if I'm given a differential equation, which we define as dy dt, or d independent, or I'm sorry, d dependent versus d independent equals a function of variables t and y. This is independent, this is dependent. Right? So the steps to do this are the following. So the first step is to set the derivative equal to 0. So when you do that, this gives curves where the values of the function is constant. You know that from Calc 1, right? When you take the derivative, set it equal to 0, you get the values where the derivative is constant, or the rate of change is 0. So these are basically the equilibrium solutions for the independent variable. And then once you do that, you're going to pick, or you're going to evaluate different sections of the plot to determine positive or negative slope. And this might seem a little, what am I talking about right now? You'll see what I mean when we look at a basic example. And, I'll give you an idea of what the behavior of a solution to a differential equation looks like. And it doesn't matter if the differential equation is separable or first order linear, which is what we're going to look at in Chapter 9. We're going to look at first order linear differential equations. or any kind of differential equation for that matter, ones that could be solved or not solved, you could use a slope field, and it depends on the differential equation. You could use the slope field to measure the long-term behavior of a solution, and that's very useful for differential equations that cannot be solved. So let's look at an example here. So my differential equation, dy dt, equals 10 minus 5y, where t is greater than or equal to 0. Alright, so the first thing I'm going to do is I'm going to set dy dt equal to 0. Right. So when I do that, I'm going to have 10 minus 5y equals 0, right? What if I solve that for y? That's easy. Add 5y to both sides. So you get 10 equals 5y, which means y equals 2. So y equals 2 is a curve where the value of the function is constant. So if I make a, if I make a simple graph, if I make a coordinate system, and this horizontal variable is t, and this is y. So what's the long-term behavior of my solutions to this differential equation? Well, y equals 2. This value here that I got just by setting the derivative equal to 0, this is what we call an equilibrium solution. It's also called an equilibrium curve. So if I sketch that on my graph, so there's the value 2. There's the horizontal line. This is the horizontal line, y equals 2. All right. So my long-term solution, so as t gets bigger, what's my solution to this differential equation doing? Is it going up or is it going down? How do I know that? Well, that's where step 2 comes in. You're going to evaluate different sections of the plot to determine positive or negative slope. Because remember, that's measuring the value of the derivative. And you learn from Calc 1 that, if I have a positive slope, that means the rate of change is going up. And if I have a negative slope, the rate of change is going down. So to do that, you just pick random values, values below y equals 2 and above y equals 2. And that's what I mean by this. Evaluate different sections of the plot. So if I pick a value that's greater than y equals 2, I don't know, pick y equals 3. So if y equals 3, that's on the positive side of y equals 2. And if I plug that in here, what do I get? Well, that's going to be what? 10 minus, what's 5 times 3? That's what is that? That's 10 minus 15, which is negative 5. So that's negative, right? That's negative. So because it's negative, everything above y equals 2 has a negative slope. So I'm putting arrows here that point down to indicate negative slope. Now if I do that below y equals 2, so for example, what I say if y equals negative 4, right? And if I plug that into my differential equation, right? So that's 10 minus 5 times negative 4. So that's what? That's 10 plus 20, which is 30. And that's obviously positive. So what does that mean? That means below y equals 2, I have positive slope. So I put arrows pointing up to indicate that. So if I wanted to draw some solution curves on this slope field, let's say I started here, right? Then as I go to the right, what's the behavior of this solution doing? Well, it's going up. So as I go to the right, it's going up. But then as I get closer and closer to y equals 2, what's it going to do? Well, as it's going up, it's going to stop increasing, right? Because I'm getting closer and closer to an equilibrium value. So it's going to get close to this curve, but it's not going to touch it, right? So this right here is a particular solution curve. If I started up here somewhere, what's the behavior of my solution going to do? Well, it's going down. And as I get closer and closer to y equals 2, it's going to hug it, right? And that's another solution curve. And I can graph as many of these as I want to. Like if I started here, the behavior is going to, it's going to do this as well, and so on. So this is a slope field. This measures the long-term behavior of the solution. So, looking at this curve, I could say, you know what? As the solution, as t gets greater and greater, so as t increases, the solutions tend to converge to y equals 2. So I'll just describe that over here. So as t approaches infinity, I could say y approaches positive 2. And what does that mean about the value y equals 2? So this right here describes the long-term behavior of the differential equation, the solution to the differential equation. And this right here, this phrase right here, y approaches 2, this is another way of saying y converges to 2. And what does that mean? Well, that means that since the solutions are going to eventually converge to 2, that means 2 is what we call a stable equilibrium. So since this is true, that means y equals 2 is a stable equilibrium solution. I'm sorry, just stable equilibrium. And you can see that because these solutions are they're converging to 2. If you're bumped off this value, you're eventually going to converge to 2, and that's what we mean by stable. If as t goes to infinity, if you were to fan away from y equals 2, that means y equals 2 would be unstable. And that's the very basic idea for drawing a slope field. It's really not much, not much different than that. So if I go to the next page in the notes, let's look at another example. My video's a little laggy, so I'm trying to, stay on top of it. But so I have dy dt equals y squared minus 16. All right, so what's the first thing you do? You're going to set the derivative equal to 0. So when you do that, what are you going to have? You're going to have y squared minus 16 equals 0. Solve that equation. Well, you could add 16 to both sides, take the square root, or you could factor it. This is y minus 4 times y plus 4, which means y equals 4 and y equals negative 4. Right? Okay, so those are my equilibrium curves. So when I make my slope field, here's t, here's y. So if I include my slope curves, or my equilibrium curves on here, so y equals 4 is up here somewhere. And down here is y equals negative 4. So now, these are my equilibrium curves. Alright, so now to determine the behavior outside of the equilibrium points, I gotta look at the slope up here, in between these two, and below this one. So just pick values. What's a value that's greater than 4? It doesn't matter. If I picked 5, right? So if I put 5 in here, what do I get? 5 squared is 25. 25 minus 16. Well, that's positive, right? I don't care about the number. It's positive. So that means above 4, my slope is positive. So I put ascending arrows to indicate that. Between 4 and negative 4, so if I pick what? If y equals, I'll do 2. And I'll do a negative value between 0 and negative 4 just to show you. But if I put 2 in here, what do I get? 2 squared is 4. 4 minus 16, that's negative 12. That's negative. So that means I have descending arrows. My slope is negative. If y is negative 2. Well, if y is negative 2, negative 2 squared is still 4. So 4 minus 16, that's still negative 12. So it's the same value. Still negative. And then finally, if y is, let's say, I don't know, negative 5. Negative 5 squared is 25. 25 minus 16, that's still positive. So that's the behavior outside of equilibrium values. So to draw some, solution curves, what if we started here? All right? What's going to happen once t gets bumped off of 0? What's going to happen to that curve? What's it going to tend to do? Well, above this equilibrium value, it's positive, right? So it's going to want to shoot off that way, right? So as I go on and on and on, eventually, it might be here, it might be down here, over here. Eventually, it's going to take off towards infinity. So, at some point, it's going to start doing that. I'm just doing this for, clarity. But it could happen sooner. It just depends. So what if my initial solution started there? What would my curve do? Well, eventually, it's going to start going down, right? So it's going to start going down, right? I'm just connecting the dots here. But then, it's going to go through here. It could cross this because, this is not an equilibrium curve. That's fine. It's going to keep going down, but what's going to happen? Eventually what? See, this is an equilibrium curve, isn't it? So it's going to get close to this, but then once it gets close to the equilibrium, what's it going to do? It's going to hug it, just like it did in the first problem. It's going to get close to it, but it's not going to cross it. So that's what one curve looks like. And let's say, for example, just to fill this in, let's say I started down here. what's it going to do on this side? It's going to go up, right? Because that's positive slope. But once it gets close to equilibrium, it's going to hug it, right? So these are long-term behaviors of this differential equation, and this is the slope field for that differential equation. So, to summarize this, it depends on let me summarize it as the following. So y equals 4 and y equals -4 are equilibrium solutions. Right? Now, in the case that, so let's look at y equals 4 first. So would you consider this stable or unstable? Well, it's fanning, so the solutions here, they're going away from that. So y equals 4 is unstable equilibrium. This is the word equilibrium. I kind of botched that a bit. So y equals 4 is unstable equilibrium. So you're either going to go to positive infinity, right? That's above the curve, or you're going to go to what? You're going to go to -4 if you're below the curve. So you're either going to go to positive infinity or -4. You're going to go to positive infinity, or you're going to converge to -4. And by similar argument, what kind of equilibrium is -4? Well, the solutions are converging towards it, so that is stable equilibrium. So y equals -4 is stable equilibrium. All right? So if you're bumped off this point right here, eventually, it doesn't matter if you're bumped off up here or down here, you're going to eventually converge to -4. So you will eventually go to -4. So, that's a good way to summarize the behavior of these solutions to this differential equation. So, when it comes to making slope fields, that's the general idea. So, that's nice and all. But, so let's go on to something new. So how do we, so question. How do we know a function is a solution to an ODE? So remember, the solution to an ODE is a function. The solution to a function is a number. I've said that several times. So how do we know a function is a solution to an ODE? Well, let's think about it, let's think about it in the function number idea. So how do we know a number is a solution to a function? What do? We plug the number into the function, right? If it's satisfied, then we know that number is a solution to the function. So using a similar argument, we can ask ourselves, how do we know a function is a solution to an ODE? Well, plug the function into the ODE, and if we get an equivalent statement, we know. That's how we know. So, suppose we have an ODE for a function I'm going to write this as y is a function of t. So then I could say, then I'm going to use a fancy symbol here. I'm going to use the phi symbol. Don't worry about it. I'm just using this for a placeholder, really. So phi is a solution to y of t, provided the following are true. So I have phi, comma, the derivative of phi, comma, the second derivative of phi, comma, all the way up to the nth derivative of phi, where n is the order of the ODE. What is the order of an ODE again? It's the derivative. It's the highest derivative that occurs in the ODE. So let me finish this statement off. So phi is a solution to the original function, provided all the derivatives up to the highest order of the ODE exist. So all I'm really saying in this first statement is that, let's say I have a third order differential equation. That means the highest derivative that shows up is the third derivative. So if I plug in the original function, the first, second, and third derivatives into the ODE, and I get an equivalent statement, then they are solutions to the ODE. So provided those derivatives exist, which in these cases that we look in this course, they will. And in the second case, so they exist, and in the second case, once you plug in, them into the original equation, or I should say the original function, y of t, you get a true statement. And that's it. So this might seem a little weird, and yeah, I absolutely butchered the word original. But it's really not that. It's pretty straightforward. If you're given an ODE and you're trying to verify a function as a solution to the ODE, take all the derivatives up to the highest order, plug them in, and if you get a true statement, you verified that function as a solution to the ODE. That's really it. Example time. So let's see here. See if I can pick something out of the textbook, or I might be able to just give you one from my own notes. So let's look at this one. Verify that the function, so phi equals 3t plus t squared, is a solution to the ODE t times y prime minus y equals t squared. So verify that this function is a solution to this ODE. So how do we do this? Well, so this is not the derivative. This right here is just t to the second power. The ODE is the derivative of the dependent variable, which in this case is y, right? Remember, if you use the derivative notation, dy dt, y is dependent, t is independent. So the highest derivative that you see here is what? It's the first derivative. So when I'm trying to verify that this is a solution to this, I have to plug in phi into y. So I have to plug phi in for y, and I want to plug in the derivative of phi in for y prime. And if you had the second derivative, if this was a second order diffie-q, you would do the second derivative of phi for y double prime, and so on. If I plug them in here, I should get t squared, and that would mean that this is a solution to this differential equation. So just, now you just got to go through it. All right. So what was phi? 3t plus t squared. What's the derivative of that? What's the derivative of phi? So take the derivative of this. Well, that's easy. That's going to be 3 plus 2t. All right? Plug these two things into here, and you should get t squared. So you're going to have t times y prime. Well, y prime is phi prime, which is 3 plus 2t in parentheses, minus y. So minus parentheses 3t plus t squared. So go through that. Distribute the t. You're going to get 3t plus 2t squared. Distribute the negatives. They're going to get minus 3t minus t squared. So when I go through that, well, the 3t and the negative 3t, they cancel out. So what? I get 2t squared minus t squared, which is what? T squared. Ha! Isn't that the right side of the differential equation? It is. Smiley face. So that means, so therefore, phi as a function of t is a solution to the ODE. That's it. That's it. Just like you would, like I said earlier, if you were doing this for functions, like how you verify a number is a solution to a function, well, you learn that in algebra. Plug it in and see if you get a true statement. Same thing here. Plug in the function into the differential equation and see if you get a true statement. And we do. So that's that part is pretty straightforward. There's really nothing tricky to it. So if I go on to the next page of my notes here, so let's go on to page 3 here. So let's look at the next thing in this section. So let me pose another question for you. Let me pose another question. So I know I mentioned this already, but not every, and it's important to know, not every differential equation has a solution. So how do we approximate a solution? My camera's trying to adjust. How do we approximate a solution to an ODE when a solution cannot be found explicitly. So how do we do this? Well, there are a lot of ways. And again, if you took a differential equations course, you'll see many ways to do this. But since we're only interested in first order linear differential equations, we're going to use a very old and very stable method, and that's called Euler's method. So let me say this. Since we are looking at somewhat simple ODEs, we'll use a simple method to approximate solutions to an ODE. Come on, camera. My camera doesn't like it when my hand gets in because it has to adjust things differently, and it doesn't like that. But I'm doing what I can, guys. Let's see. Alright, so we're going to use what we call Euler's method. So what is Euler's method? It's one of the most simplest algorithms to approximate Euler's method. It's one of the most simplistic algorithms used to approximate a differential equation solution. And it was founded by, well, you guess, a mathematician named Euler. His first name was Leonard Euler. So this is a trying to think about how to say this. A numerical method and you would see that this is a numerical method, which means we take one part, go to the next part, go to the next part, and so on. And you would see this again if you took a course in, like, say, numerical analysis. So it's a numerical method that can approximate the solution to an ODE. And it was founded by the mathematician Leonard Euler. You don't need to know that, just a little history lesson. Leonard Euler, and in the 18th century. And it's, it's pretty, it's not too hard to follow. So in order to, get an idea of how we're going to do this, I'm going to draw a graph. So let's consider this. So let's consider this. Let's say I have a graph. This is X. This is Y. Right? And let's say I have a solution curve. So let me use my markers here. Hopefully they'll write for me. Let's say that this so that right there is that's my function. Come on, camera. What's going on? I hate it when it does that. And let's say that this is my starting point. So this point right here, let's say that's my starting point on my solution curve. So that's these x of 0, comma y of 0. That's the initial point, right? Now, so just to fill this in, this is my solution. That's my solution curve to the ODE. So this is the particular solution to the ODE that I have, right? So let's say I start an arbitrary point on my curve, right? And I want to approximate that solution. So how do I do this, right? I don't, I may know the solution, I may not know the solution, right? Euler's method could be used to approximate solutions that could be found explicitly, or more importantly, for ones that cannot be found. Because, like I said, not every differential equation has a solution. So what if I want to approximate this solution? Well, so what did you learn in Calc 1? Graphically, the derivative at this point is what? So graphically, the derivative at this point is the what? It's the tangent line at this point, right? So if I took the derivative at this point, right, if I'm at the derivative, that's the tangent line to this point. So if I drew my tangent line, I have this, roughly, more or less. Right? So that's the tangent line to that point, right? It may not be exact. I mean, it's not, this is graphed by hand. So this is right here at that point. That's the derivative of y at x of 0, right? So this is the point x of 0, right? That's my starting point. So what I'm going to do is, I don't know, I may or may not be able to find the solution here, but I could take the derivative of my function. That I could do. And initially, well, that's a good approximation. The derivative is really close to the actual curve. I mean, they share this point in common. But what if I wanted to find it for any point on here? So what if I keep going with this idea? Well, if I move some increment size from x of 0, so let's say I start at x of 0 and I want to get to x of 1, right? So let's say I want to go here, right? So that right there is my next x point, x of 1, right? So the change from here to here, this little change right here, that's my step size. It's a very similar argument to Simpson's rule and the trapezoidal rule when we looked at numerical integration. It's kind of like the same idea, but don't confuse this with those two things. That was completely different. Simpson's rule and trapezoidal rule are for numerical integration. This is for differential equations. So if I move some step size here, now I'm gonna, so I'm gonna look at, and if I look at the tangent line to the curve at that point here, well, if I go straight up here, up to there, right? So if I go straight off here, and I hit my tangent line from the first solution, that's that point right there. If I make another tangent line here, Right? Just keep in mind here, I don't know. I may or may not be able to find this solution because I won't be able to solve the differential equation. But I could use the derivative of the function and get to this point. And that's what I'm doing here. I could take the derivative, put x of 0 in there, and go some step size and get here. So, what I'm saying is, this solution is the approximate solution. This right here is the approximate. This right here is the exact. If you could find this, if it's a differential equation you could solve, well, great, awesome. We don't care about Euler's method. You could do it, but we don't have to approximate it. But if this is a ODE we can't solve, this is good enough. It's better than nothing. I could use this to approximate that solution. So this right here is where Euler's method is really useful. I could use this to approximate the exact solution. And if I keep going more step sizes, I could, if I go from here to here, then from here to here, I would get another tangent line. So if I go here, let me go over here a little bit, just so it looks a bit better. So that would be x of 2, and my step size here is uniform, which means it's the same. Right. So then from here to here, there's another tangent line, which would look something like this. Right. So basically what I'm doing is I'm using the derivatives at each step to get an idea of what the solution could look like. This is the approximate, this is the exact. And you could compare the two if possible. Like if you could find an exact solution, and we're going to look at how to do that later. That's in 9.2 when we actually solve these things. So it could give you an idea to approximate the two. So this right here is, a graphical representation of Euler's method, and you could keep going with this. But so how do we do this mathematically? So I'll just summarize. This is a graphical representation of Euler's method. So how do we do this mathematically? Well, it's an iterative process, and it kind of comes from, I have a starting point, right? So here's Euler's method. If I'm given an ODE of the form, so dy dx, dy d whatever variable, equals f of x comma y, and an initial condition y at some starting point x of 0 equals y sub 0. So I have a differential equation and an initial condition. This initial condition is the starting point, basically. It's this point right here. So y sub 0, or x of 0 comma y sub 0. That's this ordered pair right here. So if I'm given this, I'm given a differential equation and a starting point. That's what this is. An initial condition is a starting point. So if I'm given that, well, what do I know about the curve here? And so what is the derivative at this point? It's the slope of the tangent line, isn't it? So we can approximate this using the slope of the tangent line. So we can approximate the solution to an ODE by the slope of the tangent line, and I'll say this, along with the equation of a tangent line. Or I'll just say the equation of a line. So when we do that, we get this. We get y sub 1 equals, so we start at y sub 0, we start here, and then we move some increment size times the derivative of the function at that point. So I start there, and that's going to be times the step size, and the step size we could represent with dx, right? That means the change in x. So that's going to be dx times the function at that point. And we could use this. So this right here is the initial y value. This right here is the step size. And this right here is the function at the starting point. So Euler's method is just, and this gives us the next solution. So this will give us the next order pair after a step size. And you just keep replicating this process over and over again as many times as you want. You could do it with 4 iterations, 5 iterations, that's up to you. So Euler's method is just doing this over and over again. So if I go to y sub 2, then I use y sub 1 plus dx times f at x sub 1 comma y sub 1. And if I want to get y sub 2, I do it for y sub 1, and then y sub 3, I do it for y sub 2, and so on. So to summarize, Euler's method is a iterative, or I'll say incremental, algorithm to get successive approximations to an ODE. So this is the word successive. So, you know, let's make this look a little bit more presentable. So if I want to approximate a solution to an ODE, if this is y sub 1, then y sub 2 will equal, like I said a moment ago, will be y sub 1 plus dx times f at x sub 1 comma y sub 1. And then if I want to get the next one, y sub 3, that'll be y sub 2 plus dx times f at x of 2 comma y of 2, and so on. until you could keep going as many times as you want here. You could literally, if you want to do it in 2 iterations, 3 iterations, usually we use 4, but the more you do, the more iterations you do, you'll see that the difference between the approximation and the exact is what we know as the error, right? This is the error. This little piece right here is the error. So, the more you do, you might see the error minimize or go up. It just depends on what the function is or what the ODE is. So you could keep doing this for as many iterations as you want, but you just keep using the previous solution to do the next one and the next one. And this is what Euler's method is. It seems more complicated than it is, but I don't think it's really that bad. It takes a little, it might take a little bit just to see how it works, but I don't think it's that bad. Example time. All right. So find the first 3 approximations. That's what we mean by, y sub 1, y sub 2, y sub 3. So we're doing this a set of 3 times. Find the first 3 approximations using Euler's method. For the initial value problem, so this might be like new terminology to you, the initial value problem. In short, us mathematicians call this an IVP for short. So if I say IVP, we mean initial value problem. And all an initial value problem is you have a differential equation and a initial condition. That's all it is. And that's why it's called an initial value problem. So I have an initial value problem of, let's see, dy dx equals y e to the x. And so that's the differential equation, and the initial condition is y at 0 equals 2. So we're using Euler's method to approximate the first 3 solutions of this differential equation with this starting point, or initial condition. That's what we mean by IVP. It contains this and this, with a step size. We have to have a defined step size. That's up to us. And the problem dx equals 0.5. So a step size of a half. Alright, so we're doing the first 3 approximations of Euler's method to approximate the solution. Now, a question you might ask yourself is, well, could I solve this differential equation? Do I know how to solve it? Yeah, actually you do. If you think about one of the first kind of differential equations we looked at in this class, what kind of differential equation is this? it's separable. This is a separable ODE, right? You could get the y's and the x's by itself to integrate both sides and solve for y, right? And you could solve this, and then plug in this to get the value c for the constant, and you'll get a function, right? And then if you plugged in a value, you could compare that to the approximations. So yeah, you could compare the exact solution versus the approximate solution, but we're not going to do that. We're going to use Euler's method. So I want to find the first one, then the second one, and the third one. So the first one. So what's the first solution? Well, it's going to be y sub 0 plus dx times f at x of 0 comma y sub 0. Come on, camera. You could do it. There you go. I don't know why it does that. Alright, so what is y sub 0? It's 2. This is x sub 0, right? That's x sub 0. This is y sub 0. Alright, so y sub 0 is 2. Plus, what was my step size? 0.5. And that's going to be times the function, which is my differential equation, evaluated at 0, comma, y sub 0. So this is going to be my function evaluated at 0. What? Let me use function notation here. This is f. Evaluated at what? What is x of 0? It's 0, comma, 2. Alright, I know this is a weird looking f, but let's just write it out that way first. So 2 plus 0.5 times, so if I plug this ordered pair in here, what do I get? What do I get? So when x is 0, right, so that's e to the 0, which is 1, and 1 times 2, right? So then 1 times 2, that's going to be, so this will be, I'll just write it all out, this will be 2 e to the 0, right? So if I go through that, I'm going to get 2 plus, well, there we go. E to the 0 is 1. 1 times 2 is 2. What's 2 times a half? Well, half of 2 is 1. 2 plus 1 is 3. So that means y sub 1 is 3. How do I get x sub 1? How do I get x of 1? Because I'm going to need these to go to the second iteration, right? That's going to get the second iteration. Well, I get x of 1 by, so what did I start at? I started at x of 0, right? And then to get to x of 1, I'm going to add my increment size. What's my increment? 0.5. So I'm going to add dx. So to get to x of 1, that's going to be my starting point for x of 0. Well, my starting point for x, which was 0, plus my increment size, which is 0.5. So that means x of 1 is 0.5. So now, x of 1 is 0.5, and y sub 1 is 3. So now this is my new point on my curve, right? If I look in the previous notes, right? So in this example, right, this point right here was my starting point, right? Now the point I got here, so this ordered pair, 0.5 comma 3, is my next point on the curve, which is going to be this point. It's an approximation. But I could compare this to the exact value if I solved this by separation of variables and went through that, but I'm not going to do that. So now just go to, now you're just going to repeat the process again. So y sub 2 equals what? y sub 1 plus d sub x times f at x sub 1 comma y sub 1. That will give me my second approximation. What was y sub 1? 3. Plus, what was my increment size? My increment size never changes. That's 0.5. Well, it never changes in Euler's method. And then this is going to be the function evaluated at one point. This will be the function evaluated at 0.5, comma, 3. So when you go through that, you're going to get what? You're going to have 3 plus, so 0.5 times, so when I plug this into my function, what do I get? I get, so my function was y e to the x, so, or y times e to the x, I should say. So y here is 3, so I'm going to have 3 e to what power? 0.5. So if you do this computation, you could do that in your calculator, right? Then you're going to multiply it by 0.5. So 3 e to 0.5, 3 e 0.5 gives me 4.94. So, you know, whenever you're doing these things, you know, usually the number of decimal places you round the value to, you know, it just depends on the textbook or the instructions. In your textbook, it says to round it to the 4 decimal places. So I guess we'll just do it. I guess, I mean, it really doesn't matter. We're going to do it to 3 decimal places. So 4.946. So that's what this is, right? So, you know, I'll use this value in here, but the whole answer all around to the, you know, 3 or 4 decimal places. It really doesn't matter. So that's this value. Multiply that by 0.5. I get that. And then add 3 to that. So when you go through that, you're going to get approximately 5.473 as y sub 2. So that means y sub 2 is 5.473. Right. And what's x of 2 going to be? Well, x of 2 is going to be what? So I started at x of 1, and now I'm going to add point. So x of 1 was, and then I'm going to add my increment size to it. So x of 1 was 0.5, then I'm going to add what? 0.5 to that. So that's going to be 0.5 plus another 0.5, which is 1. So to summarize this, now I'm at the I'm at the next iteration, which is going to be, so x of 2 is 1, and now y sub 2 we just found to be what, 5.473. So that's the next order pair in my process, right? So this order pair is, so we started here, we did 1, and now that's this one, and then we're going to do it one more time because we want to get, the instructions say we want to get 3, right? So do it one more time. Alright, so y sub 3 equals y sub 2 plus my increment size times my function at x of 2 and y of 2. This is just Euler's method, just repeating it over and over again. So y sub 2 is going to be 5.473 plus my increment size, which is 0.5, times the function at what? X of 2, which is now 1, right? comma, y sub 2, which is 5.473. So when you go through that rigmarole, so what's this going to look like? It's going to look like what? Y times e to the x, right? So this is going to be y times e to the x. Well, y is 5.473 times e to the x. Well, x is 1, so that's going to be e to the first power. All right, so whip out your calculator here. So 5.473 times e, and I'm going to use the approximation because that's what we're doing, and that times e to the first. And that gives me 14.88, or well, we did it to 3 decimal places, so 14.877, but I'm going to multiply that by 0.5. Gives me that, and then I'm going to add 5.473 to that. So plus 5.473. That gives me an approximation of 12.912. So that's what y sub 3 is. Right. And again, if I wanted to get x, so this is the, this is the third approximation that we were looking for, right? We want to find the first 3 approximations, so we found the first one, the second one, and the third one. There's the first approximation, this is the second approximation, and this is the third approximation. So, if you went through this, initially it doesn't look like this value is going to anything, right? It doesn't look like it's going to anything in particular because we only did 3 iterations. But the more and more iterations that you do of Euler's method, this value is going to, potentially converge to the true value. In other words, the gap between the exact value and the approximate value will start to shrink. And you're going to get, you're going to get a better approximation, in good cases. And most of the differential equations we look at here are going to be, good cases. So just to summarize this problem, this is the first approximation. This is the second approximation. And this is the third approximation. And if you're curious, you could you could solve this equation, right? You could solve this differential equation, right? Separation of variables, and plug in 0 and see what you get. See how that compares to this. Well, actually, you should get 3, because, right? If I go back to my notes, you should get 3 because the approximate and the exact are the same thing at the first point, but then afterwards they start to change. So a good thing to do is, if you solve this differential equation and then plugged in 0.5, right? I'm sorry, don't plug in 0.5, plug in 1, right? If you plugged in 1, see how that compares to this. This is the approximation. See how that close that is to the exact value. And, but that's Euler's method, That's Euler's method. And, it's pretty convenient. It's not always, it doesn't work for every kind of differential equation, but it will work for the ones that we look at in this class. All right. So that's it for the notes for when it comes to 9.1. That's it for 9.1. So I'll stop the video there, and in the next video we're going to go to 9.2, which is looking at how we're going to solve first order linear differential equations by hand.